Let's see how much we can get through in one video. So these are the solutions to some questions in the book about work, force, and distance. Okay, so this was from page 161. Okay, let me put that back to page 161. I was flipping ahead to E equals MP and MGH. Okay, so 98 Newton rock, going tobogganing, pushing it 2 meters. Okay, so we had force, distance, work. Trying to find work. Punch in your numbers. And luckily for us, our answer had 3 significant digits, 1, 2, 3, 1, 2, 3. So we didn't need any rounding, so we were good to put that in a box. Okay, 6. They gave us 25 newtons of force, 2 meters, okay, with 3 significant digits, 1, 2, 3, 1, 2, 3. Tried to ask us what the work was. So we use work is force times distance. So I put them side by side like this, just so you can see it in a different way. And the answer ended up being 50. Okay, given that we have 3 significant digits though, we actually need to add 1. Okay, so we added 0 to get the right answer. Number 7, you can pause this if you actually want to read it a bit better, that would be a good idea. So you had 43 joules of work. You moved at 3.2 meters across the floor, and how much force were we working with here? Number 8 was 2 times 10 to the 4 joules of work. The force was 1.2 times 10 to the 3 newtons. And how high in distance did we lift the object? Okay, so your answer is here. Okay, so the only main difference from the top questions to the bottom is what you're looking for. So force has a slightly different formula, goes on top, divide them. Make sure you round it the right amount for 3 significant digits for the units. And with 8, we were looking for distance this time, and we were working with scientific notation. Okay, so when you were punching that in your calculator, okay, you were using the 10 to the what button. Okay, so this was 2 shift 10 in my calculator to the 4 times 1.2 times 10 to the 3. Okay, and this was your total. And if you don't trust it, because you pushed times instead of divided by like you're supposed to, you can go back and put the right operation. Okay, and you get 16.66666. And if you don't trust the scientific notation, you want some more practice, okay, you can push this to make sure you know what that is. And you can push this to make sure you know what it is. And you can do that one divided by that one. So 20,000 divided by 1,200. Okay, you can see the same number. Sorry, you couldn't see half that. Okay, so what we did was we put 2 times 10 to the 4 was this. 1.2 times 10 to the 3. Okay, we divide them just to make sure it's the same answer, just so we can trust our calculator. Do you need to do that every time? No. Okay, but we're new at it, so that's what we're going to do it. And let's check our notation. So it should be 3 significant digits. 1, 2, 3, 1, 2, 3. So our answer needs to be in 3 significant digits. And we don't ever put a repeating in our answer. Okay, we do some rounding. So that's that. Now let's see how much of this PowerPoint we can do. This one is about acceleration. Okay. So what is acceleration? It's a change in velocity during a specific time. Vector means it has a size, like a magnitude it's called, and direction. And the graphs matter as well. Okay, they're different, and you're going to read them with time as your on your x-axis and speed in meters per second on your y-axis. Okay, so what's going on is if something's speeding up or slowing down, and if it's moving in a positive or negative direction. And positive and negative direction just means like forwards and backwards. Okay, so when you're calculating the acceleration, you're going to do the change in velocity. That's this little delta. Okay, and change in time. So how to figure those out? You take the final, this little f means final speed, minus the initial velocity, and it's so speed with direction is the velocity, and final time minus initial time. Okay, so 6 minus 0, right? 6 seconds. And then you're going from this speed to this speed. So you put this one, okay, the final speed minus the initial speed divided by seconds, right? So it's very important to show your steps along the way, because if you accidentally put this one first and this one second, you're going to get a completely different answer. Okay, so do one step at a time. Just calculate your change in velocity. Okay, and the only reason this wasn't calculated here is because your initial time was 0. Okay, otherwise you would have put final time minus initial time. Okay, and so 65.6 minus 15.2 is 50.4. Divided by 6, 8.4. Okay, now is it actually that? Check with your calculator, because it might have been rounded for significant digits. Let's look. Yeah, it actually was 8.4. Perfect. Okay, and if you're looking at the unit analysis, you have meters per second, okay, which gives you, we don't put things in per second, right? So that's like meters per second times 1 over seconds. So we end up with meters per second squared. Here's some examples for you. So we're going from rest to a velocity of 50 meters per second. So rest is 0, upwards in 4 seconds. What's its acceleration? Now, I always make you do all your steps, okay, but just for the purpose of speed, okay, we're going to go A is change in, stop autocorrecting, I want lowercase, okay, is change in velocity divided by change in time. Okay, so we should be able to go with 50 divided by 4 is 12.5. So work through that as well. So you're pausing these. Same thing with this. Give it a try on your own. And then look at the answer. Meters per second squared is going to be your answer. Let's always put our solutions. Where's my superscript button? Okay, so make this go up. Okay, so it should be per second. Not with the big 2, with the little 2. Okay, well, I guess I'll just leave that there. And the car driver is going to slow the brakes down from 15 meters per second. This should go here. East to 5. So 5 was the final. And 15 was the initial. Okay, so it's going to be negative, because negative means you're slowing down. Okay, so minus 10 divided by 4. Okay, so this negative just means it's slowing down. Okay, here's some rearranging equations, but I like for you to just have them available to you. Hey, look, Betty's in this question. Look, Betty, you're in the question. Pretty cool, hey? And she hits the brakes to round the corner safely. And it takes her 5 seconds. So what was her change in velocity? So this time you're just rearranging your formula a bit. So V is going to be A times T. Okay, so 0.5 times 5 is 2.5. Okay, and if you don't understand why this is the right answer, ask. Okay. Right, and then let's do these together, because I'm worried you won't do the video otherwise. Okay, practice, practice textbook. Okay, here's some graphs that we'll look at a different day, and more practice. Okay, we still have 5 minutes, so let's see what was in the other one. Calculating work and energy. Okay, so what this is about is if you do 10 jumping jacks, is that any work? No, if there's no distance. Okay, if you actually move the wall, yes, the work is being done. Okay, so the net force has to be applied, like a push or a pull, and it has to actually move. Okay, so Baymax here is actually moving the ball, work is being done. Okay, so if you're pushing a sharp end card, is it moving? Yes, there's a distance, so yes, there's work being done. Sleeping, nope, no distance. Writing in a notebook, we always say that's work, but the notebook's not moving a distance. Maybe your hand is, so work would be done there. Holding a yoga pose feels like work, but according to our definition of it has to move, okay, then no. Lifting a pencil off the floor, yes, work. Holding a heavy box might feel like work, but there's no distance, so it does not count as work in this example. Okay, so in our calculations videos, we had written this down on our special physics sheet of science. Work is force times distance. Force is measured in newtons. Distance is measured in meters. And work is Newton meters, which works out to a joule. Okay, which is also energy. All right, so if we lift this up, okay, work is force times distance. So that's going to be, show your work, of course, but to double check it, okay, that's going to be your final answer. Okay, and this one, your final answer is going to be, I'm just going to make sure I put this properly. Yep. Okay, so 9.75 times 10 to the 1, 2, 3, 4, 5. Okay, so pretend this is a pie like this one. And you're going to put it in joules. Okay, or you could also put that in kilojoules. So it's 975 kilojoules. So if you want to rearrange the formula, great. Okay, then you'll have some different examples. So we have work and we have force. So we're going to use the distance. Okay, so distance is going to be work divided by force. Okay, we always want to show our work, but for the purpose of the video, okay, we're going to put the answers. 3 significant digits, 3 significant digits. Okay, and this is a crane. What's the force? The force is going to be work divided by distance. Oops. Sorry, camera. Times 9.5. Okay, so again, make this superscript. Let me see if I can remember how to do that. No, I can't remember. I'll have to look that. Oh, found it. Here it is. Here we go. Okay, so there's your final answer. Last one about graphs. Okay, work is the same as energy. So if it says what's the energy, then it's just the same. Okay, so in real life, there's friction that messes things up. But luckily for us, we have, we're only working on grade 10, so we don't have to calculate for friction here. Okay, efficiency, we're going to do a different day. And we have some practice problems. Just in time.